Welcome everyone in the new lecture of stresses in rigid pavement. As maybe some of you already know about, we have three basic type of the stresses which are produced in the rigid pavement. Number one, when we have the stresses occur due to wheel load. The second one is because of the temperature, while the third one is when we have the stresses induced due to the moisture variation. This specific lecture is about when we have stresses occur due to wheel load, and we will also try to understand the phenomena that how we can determine the stresses in different location through Westergaard Slab analysis. So stay tuned with us. As you can see here, wheel load is moving, is a moving load which change its position over concrete slab. As a result, which also induced in concrete will also change different location as well. So it became necessary to investigate the critical position of a wheel load or the concrete slab, which will also induce the maximum tensile stresses. Okay. So when wheel actually move, the location of the stresses also change its position from place to place. So in this specific lecture, we will try to understand that is it possible to determine, for example, if we want to analyze the stresses at center, at edge, at slab corner, is it possible? If yes, then how? Okay. So Westergaard come up with the assumption that of course that's why it's called the Westergaard slab theory. So Westergaard proposed expression for these stresses for various critical position of the wheel load on the concrete slab. So he assumed he present his theory while assuming few factors. Okay, the very first one is that the slab is homogeneous, isotropic, and elastic solid in equilibrium. Okay, and also we have the slab thickness is also uniform, while the second one is that the subgrade reaction are vertical only, which is proportional to the deflection of the slab in vertical direction. So as maybe you if you already followed my previous lecture, when we want to determine the bedding modulus, which is equal to K. So in the Westergaard slab theory, bedding modulus is equal to stresses over the deflection. Okay. So and also the third assumption is that the slab thickness is uniform, while the fourth one is a single wheel load is considered which is uniformly distributed over a circular area in the interior of the slab for corner of the at the corner position. In case of the corner, the circumference of the contact is tangential to the slab edges, while the last assumption is that the weight of the single wheel load for edge of the slab is considered to be distributed uniformly. Okay. So according to Westergaard, few cases were considered. So is here you can see Westergaard also analyze the three critical location of the wheel load, which named as interior location when the distance of the wheel load is more than 0.5 meter from the slab edge. That specific position is called interior location, while he also assumed location which is also critical at the corner location as well as at the edge location. The stresses for those location are given by different type of a assumption. Okay, so first of all, he came up with three basic position. The number first one was the interior location of the slab, where the tensile stresses were developed at the bottom of the slab, while the second assumption was when wheel load is at the corner position, so how tensile stresses will induce at the top of the slab, while the third assumption were when the wheel load is at the edge location or at the edge of a slab, so then how the tensile stresses will occur at the bottom of the slab. So that means when the load is acting at three different locations such as center, edge and corner, So how much it is affecting the bottom of the slab, or how the relation of the stresses are transferred from the top to the bottom. Okay. So later on those equations were modified again by Westergaard and some other different researcher, which is called Westergaard modified equation or Westergaard slab theory. So the purpose of this figure is just to give you that, for example, if this is our slab and we would like to determine, is you can see through the arrow, the interior position, or we can call it the center. We can also determine it at the edge. We can also determine it at the corner of the slab as well. So keep in mind one thing, that the effect of stresses at any section across the slab will be completely different. Okay. For example, keep in mind the most stable position will be at the center of the slab, where the load could be distributed properly, while the most critical portion will be at the edge as well as at the corner as well. Okay. Stay tuned with us. We will also try to determine that how the discontinuity could occur when the load is transferring at the slab edge as well as at the slab corner as well. Okay. As here you can see, Westergaard come up with the slab theory analysis, through which we can determine the maximum flexural stresses which occur due to the wheel load which are acting on the slab. As you can see here, we can determine it through center, through edge as well as through the corner. For example, so all those assumptions which are just like mentioned here. So the sigma is denoted with the for the flexural stresses, while Q is basically the wheel load. Okay, while mu is a Poisson ratio, while H is a slab thickness which will be provided in the millimeter, while K is the modulus of the subgrade reaction. Okay. And A is basically the radius of the contact area, while L is the radius of the relative stiffness. Okay. Which will also be mentioned sometime. And also we have another indicator, as you can see here, in the center as well as in the edge, the another factor which is called B. So B is basically the radius of equivalent pressure, which will be considered as the distribution at the bottom of the slab layer. Okay. So just to give you a little bit idea, so we can also determine, so just assume that how we can analyze the bedding modulus value of K. So we should consider the wheel load which is acting from the top, okay, in the circular position. So we can determine the contact pressure. Q is basically load, while pi is already given 3.14, while A is a radius. So we can determine the value of a K. So how we can determine the value of a K? We can determine the virtual bedding modulus when we consider the E2, which is basically the Young modulus of the subgrade layer, divided by the total thickness, which is H1. So according to the OD mark, we can determine if we have the bounded or unbounded layer. So this is another type of a assumption which we will try to understand in the coming slide. But for the time being, so C is a coefficient which we consider for asphalt 0.9, while for the concrete layer we consider it 0.83. So here is you can see here it's quite clear mention, it's a concrete layer, so we will consider here 0.83. Okay. You can see here, so if we want to determine the bedding modulus with the granular unbounded side. Unbounded base layer means when all the layer are basically acting like as we already mentioned, all those formula which were mentioned, which were actually used in the previous formula. For example, if you want to determine if you want to apply the Westergaard Slab theory, okay, at the center, edge and the corner. Okay. So just a different parameter, like H shows is a slab thickness, E is a elastic modulus, and mu is a Poisson ratio, F is a wheel contact area, while P is a contact pressure between wheel load and the road surface, okay, and so on. So this is our very first numerical or like tutorial. Here we have a condition given when we have the top layer thickness is 200 meter and E1 is 30,000, while mu1 is 1/6, while the Young modulus of the subsoil is 100. Okay, so what is our task? We are trying to determine the bedding modulus. So we have a clear formula. K is equal to E2 by H1 static. So to determine the H1 static, we have a formula of a C1 dot H1 into the square cube of E1 divided by the subsoil Young modulus. Okay, so as you can see here, we determine the H1, and similarly we can also determine the bedding modulus as well. Okay, so in that specific condition we have 0.09 or bedding modulus. So if someone tell you that you also need to do, draw the model for the Westergaard as well, so the same sketch should be like repeat and like revise, but in the last you just need to mention that bedding modulus or K at the subsoil is 0.09. So you must need to mention it as like. This is the second condition when we have the two unbounded layer system. Okay, so keep in mind one thing: to determine the bedding modulus for the bounded and unbounded layer, we have completely different way to determine the bedding modulus. So we have the concrete layer, and then we have the unbounded layer, and then we have a subsoil condition. So to determine the bedding modulus, we have a formula K is equal to E3 into H1 static plus H2 static into H1 static into H1 plus H2. To determine H1 is, we have a clear formula of C1 H1 into E1 by E3. Similarly for the H2 layer as well. Keep in mind one thing: in both condition of H1 static, to determine the effective height for H1 and H2, here we use the E3 factor value. E3 is basically the Young modulus of the supporting layer, because we would like to determine the bedding modulus at the lower layer. So we should consider the overall Young modulus, okay, which is basically supporting all those three layers together. Okay, this is one important and conceptual thing which should be keep in mind forever. And then we have a third condition when we have the bonded bedding modulus condition. Okay, so here we come up with a new type of a geotextile. So if we have a geotextile layer is already installed below the concrete pavement, while above the cement treated base layer. But just to give you a little bit assumption, so we are trying to remove or like neglect the elastic properties of the geotextile. So is to analyze or to determine the bedding modulus. Similarly, we will use the bonded formula. As you can see here, first of all we will determine H1 and then H2. So to determine the H static, just we need to add H1 static plus H2 static. Okay, and similarly to determine the bedding modulus, K is equal to E3 by H static. So we can get the subsoil condition of the bedding modulus at the supporting layer. So now we reach to the, so far we try to analyze the tensile stresses when we have a bonded or unbounded condition. We try to determine it for the single layer, for the double layer, for and like as well as for the three layers. So now we are in a stage and we are trying to determine when we have the bending tensile stresses of a rigid pavement, and we would like to determine it the tensile stresses at exactly at the center as well as at the corner as well as at the edge. So The question is it possible? If yes, then how? Okay. So, the given data is H1 is already mentioned, Young modulus is you can see here. Okay, keep in mind whenever you are trying to resolve the Westergaard, or for example the pavement design analysis, you just need to come up with a very clear sketch so that to like mention all the parameter which is already assigned or like given. Okay, so then it will be like really easy, because we have already formula, like set of formulas. Okay, so you can just determine that which parameter you need to identify and which parameter like you have already. So the task will be little bit more easy. As you can see here, as we already mentioned all those formula before, so we have a center, edge and corner. Okay, so we can determine it, but keep in mind here, here we have one assumption. Okay, to determine the A is, we already mentioned, A is basically the radius of the contact area. Okay, so if we want to determine B, so for B it is the formula is already mentioned, but to reach to that B, so first of all we need to determine the radius of a contact area. As you can see here, this is our very clear model sketch through which I try to resolve the same problem. So as you can see here, we have the given load of 50,000, and then we have the contact pressure between both surface, which is 0.7, and then we have the height of the concrete layer is also mentioned. Okay. At the other side, as you can see here, so here I try to sketch a clear slab for the better understanding purpose. So our task is to determine the modulus or the stresses at the center as well as at the edge as well as at the corner. So we have formula as you can see here, 0.75 into q dot by h square into 1 plus mu into log of E h cube dot by kb4. So as you can see here, all like almost all those parameters is already given. We have already wheel load, we have already h, we have mu, we have E, we have like the value of the thickness. The two parameter which we don't have, we need to determine those. Number one is K, second one is B. Okay, what is K? K is basically bedding modulus, which we will determine through the formula, which is E2, which is basically the Young modulus of the subsoil divided by the H1 static. So as you can see here, we have only one single height of the slab, so we will consider it a 200 mm. Okay, for that purpose, we are going to use our bounded formula, which is equal to C1 H1 into E1 divided by E2. Okay, so E1 is, it's quite clear, we have the condition for the concrete, so we will use the coefficient for concrete, which is 0.83 into 200. So from here we determine the H1 value is 111.26 mm. Okay. So if we want to determine the bedding modulus, so K is equal to E2 divided by H1 static. So from here we can determine easily the value of the bedding modulus. Okay. From here we also would like to determine the value of a B, because we have now the radius of a contact area. Okay, so we would like to determine the also radius of a equivalent pressure which is distributed at the bottom of the slab. For that purpose, first of all we have a radius of a circular area which is equal to A is equal to Q dot by P into pi. Okay, so we have Q, we have P. So from here we can determine the value of A, which is almost 151 millimeter. Okay, so as you can see here, we would like to see that if the factor is less than of our value, then we don't need B, but if it's less than of A, so then of course we will come up with the to determine the value of a B. So what we will do, so 1724 into the total thickness of the height of the slab thickness, which is 200, so it is equal to almost 34,480 mm, which is above than our value. So here we have a formula which is equal to, so from that specific formula we can also determine B. Okay, so now almost we have all the parameters. Okay, we have Q, we have H square, we have mu, we have E, we have H cube, we have K, we have B as well. So through analysis of that equation, we can determine the tensile stresses at the center. Okay. Similarly, we will also use the to determine the tensile stresses at the edge as well. So almost we have all the parameters, as you can see. We have Q, H, mu, E, H, K before. So you just need to put all those values. So through this method, we can determine the tensile stresses at the edge as well. And similarly for the corner as well. So you can see here we have all the value is almost given, so we can determine it easily. So I hope that you have learned today's session, and you also understand that how we can determine the bedding modulus of different condition when we have the bonded layer system, when we have the unbonded layer system, and also you have learned that how we can determine the slab stresses at corner, edge, as well as at the center of the slab. Okay. For more lecture, please stay tuned with us. Thank you very much.